Welcome back to my fourth session, and today we will tell about the calculation of capacitance. Myself, Dr. Sayanti Chatterjee, Associate Professor of Institute of Aeronautical Engineering, EEE Department. This is in your Unit 2, the calculation of capacitance. So, the course outcome of this is to demonstrate or apply the behavior of conductors and dielectrics, and therefore we can compute the capacitance of different configured plates. So, capacitance in our electrical engineering, resistance, capacitance and inductance are the main three components. We know what is resistance, what is inductance and what is the capacitance. But today we will study of the different types of capacitance and how we can use it, how we can design it or we can describe it from the view of the electromagnetic field. So what is a capacitance? Capacitance is the ratio of the charge enclosed or stored to a conductor to the volume. So we can write that the C equals to Q by V. So what is C? C is the capacitor. What is capacitor? Capacitance is the ratio of the amount of electric charge stored in any conductor to a difference of the electrical potential. So what is C? C is the charge. And what is V? V is the potential. So this is known as the capacitance. Now we can write the capacitance using the symbol C, and its main unit is farad. Another, whatever we are using for our daily life, the capacitance ranges mu F means microfarad. Microfarad means 10 to the power minus 6 farad. Microfarad is 10 to the power minus 6 farad. Then is nanofarad. What is nanofarad? Nanofarad means 10 to the power minus 9 farad. And last one is the picofarad. Picofarad means 10 to the power minus 12 farad. So, though farad is the most known unit, or farad is the main unit of capacitance, we can also divide it into the three subcategories for our problems for our daily life: microfarad, nanofarad and picofarad. And what is the derivations? Already we have discussed. Capacitance is equal to charge stored in a conductor divided by the voltage difference or potential difference between two ends. And if we want to tell it in the form of the our field theory, we can little change. We know charge Q is equal to, we can write rho L into L. What is rho L? Rho L is nothing but the line charge density, charge per unit length. So this is the line charge density, or into L, total length, is equal to, we can write rho S into S. What is rho S? Rho S is equal to, known as the surface charge density. This is the surface charge density, or we can write it rho V into V. What is rho V? Rho V is the volume charge density. So Q can be defined as three types. One is the line charge density, surface charge density and the volume charge density. Next important thing is, according to the definition, C is equal to charge by voltage. So what is voltage? According to the field theory, E is equal to according to the field theory, voltage potential difference is equal to E dot dl. What is E? What is E? E is the electric field intensity. What is dl? Dl is the total length. So from there we can write the charge is equal to Q by V is equal to, we can write Q by V can be written as rho s into S divided by E dot dl. This is the another definition. This is the another important definition of the capacitance. Capacitance is equal to Q by V is equal to rho s by S E dot dl. So there are the same definition we are getting from different term. So this is the first is the C is equal to charge by voltage, and we can write it as rho s into S E dot dl, or we can write rho L into L E dot dl, or we can write it rho V into V E dot dl. So these three types we can write the charge. So this is the definitions of capacitance. So first we will start from our very basic definition. What is that? That is the series and shunt connection of the capacitance. You can see from the diagram C1 to Cn, the n number of capacitance are connected in series. And what is the equivalent? Equivalent is can be written as 1 plus C1 plus 1 plus C2 and up to Cn. And the C equivalent is the reciprocate of the equivalent 1 by C total. In the case of the parallel, you can see the capacitors are connected in parallel or shunt. We can call it parallel also. So shunt connected or parallel connected. So as they are in the parallel connected, you can see C1, C2, Cn up to n number of capacitances are connected in parallel. So what will be our equivalent capacitance? Equivalent capacitance will be C1 plus C2 plus C3 up to Cn. So this is the shunt and series connection of the capacitance. Let's solve a problem. So you can see in the one case there are three capacitance. So these three are connected in series. How to understand series? If we think the current is flowing, the same current is flowing through the three capacitor. So according to the formula, what is C equivalent? 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. What is 1 by C1? 1 by 12 plus 1 by 20 plus 1 by 30. And it is coming 65 plus 3 plus 2. So it is 10 by 60. So this value we are getting as 6 microfarad. We are getting the value 6 microfarad. 10 by 60 means 1 by 6. 1 by 6 microfarad. So what is C equivalent? C equivalent is equal to opposite of this, and this is coming as the 6 microfarad. The answer is 6 microfarad. 1 by 12 plus 1 by 20 plus 1 by 30. Next, if we think about the shunt. Shunt means if we think the current is coming at the branch and it is dividing into the three parts. 1, 2, 3. So this is the shunt. And in the case of the shunt or parallel capacitors, the equivalent capacitor is 12 microfarad plus 20 microfarad plus 30 microfarad. This is the simple addition and it is coming as 62 microfarad. So for the, this is the shunt connection. So for the shunt connection or parallel connection, these are the three addition, 12 plus 20 plus 30. So it is basically the 62 microfarad. Already we got the value. Now we will discuss the most important thing of this unit is the capacitance of parallel plate capacitor. And this is not only used for the theoretical thing, it is also full of problems. Different types of sums will come from here. For the next class, we will discuss the sums or problems from this chapter. So now we will discuss about the parallel plate capacitor. What is the meaning of parallel plate? But you can see there are two plates. The top portion is the one parallel plate and the down portion is the another parallel plate. This brown one and the down side, this brown, these two are two parallel plate. And what is A? A is the cross-sectional area. What is A? A is the cross-sectional area or surface area of these plates. This is not cross-sectional. This is the surface area of the plates. So what is A? A is basically the surface area. A is basically the surface area of the, A is the surface area of each plate. And for our simplicity, we will assume that the both plate has the same amount of the surface area. Now the thickness or the distance between these two plates is given as D. What is D? D is the distance between the two plates. D is the distance between the two plates. And we are assuming that in between the two plates, it is full of the dielectric material. So any dielectric material can be there. So D equals to the distance. D is the distance. And what is the blue one? Blue one is the dielectric material. This is the dielectric material. This is the dielectric material. And we know in the case of any dielectric material, we can write the permittivity of the dielectric material is equal to epsilon 0 into epsilon r. What is epsilon 0? Epsilon 0 is the permittivity of free space. Permittivity of free space. And what is epsilon r? Epsilon r is the relative permittivity. What is this? This is the relative permittivity. Now you can see from this real life, this is the true parallel plate capacitor. You can see this is the conductor, this steel conductor we are using here. This is the first conductor and this is the second conductor. They are fixed on a, this is a stand. On a stand or on a stand it is connected. And in between there is some air. And we are using the air as the dielectric medium. Here we are using the air as the dielectric medium. And we are assuming that the cross-sectional area of this plate is equals to the cross-sectional area of these plates. So both are equal and this is the air. and this is our A. This is the A, the surface area of this. This is the distance between these two is D, and as this is the air, we can write the permittivity is only epsilon 0. So we can write from here that since the capacitance is the ratio of the electrical charge and the potential difference across the plates, we can write C is equal to Q by V. What is C? C is equal to Q by V and unit is farad. Now, we are thinking about the parallel plate capacitor. So, in the parallel plate capacitor, we already know from the Gauss law, what we know? We know that the flux density, what is D? From the Gauss law, D is known as the flux density, or we can tell it is the electrical flux density. What is this? Electric flux density. So we know the electric flux density D, and what is the formula? What is the definition? Q by A. So what is the electric flux density? Electric flux density means charge per unit cross-sectional area or unit surface area. Flux per unit surface area is known as the electric flux density. So this is the D. And another relation we know from the unit 1, D is equal to epsilon 0 into E. What is D? D is equal to epsilon 0 into E. So if it is air, we can write epsilon 0. If we are thinking it is not an air, so it will be D equals to epsilon into E. Already we know this formula. So what is E? E is equal to Q by A. Q by A means D divided by epsilon. So what is E? E is equal to D by epsilon. Already we got this. Now, according to the definition of potential also, if we not taking the sign, so V equals to E into D. We know V is equal to E into D. What is D? D is the distance. So already we know E, if we substitute the value of E, Q is equal to E naught or epsilon naught A into D. We already got this value. Now what is capacitance? Capacitance is, according to the definition, Q by V. What is capacitance? Capacitance is equal to charge per unit potential is known as the capacitance. So what is V? V is equal to Q by C. So if we substitute the value, we can get C equals to Q by V. C equals to Q by V. So Q by QD epsilon 0 into A. Q cancel out and C equals to epsilon 0 A by D. So this is the capacitance of a parallel plate capacitor. C equals to epsilon A by D, where A is the surface area of each plate and D is the distance between them. So what is capacitance? Capacitance is equal to epsilon A by D if the medium is other than air. In case of air, we will assume epsilon 0, but if it is other than any air or vacuum, we will take it as the epsilon, and equals to K epsilon 0 A. What is A? This is not K actually. This is known as kappa, and this is the one constant term. What is the name of this constant term? This is known as the relative permittivity. We can write it by Fr. This is also known as the relative permittivity. Now we will discuss a small problem from here. Okay. Before problem, another one is there, that is the capacitance of a coaxial capacitor. This is another very important topic in the case of a capacitor. So what is this? The capacitor can be defined as we know the basic. First we will start from the basic. Capacitance is known as the C is equal to Q by V. This is our basic equation. Now we are thinking about a coaxial cable. What is the meaning of coaxial cable? Two cables or two cylinders are there and their main axis are same. One cap is, if this is the pen, we can think that this inside one, this one, a nib is the one capacitor, one cylinder, and the outer side is the another cylinder. But in the case of the both, the axis is same. You can see this is one cylinder, this is the another cylinder, and they have one common axis. The best example of the coaxial cable is the underground cable. So here we can assume that the L is the length of the coaxial cable. What is B? B is the radius of the outer circle. So there are two circles. B is the radius of the outer circle, or we can tell B is the radius of the the larger cylinder. What is A? A is the radius of the smaller one, smaller circle or the smaller cylinder. So we have two coaxial capacitor. Okay, and we are assuming that epsilon r is the, what is epsilon r? Epsilon r is the relative permittivity of the medium. If it is air, we will take epsilon r is equal to 1. So epsilon r is the relative permittivity of the medium. So the total value is epsilon will be epsilon 0, epsilon r. So what will be the value? It will be epsilon 0, epsilon r. If the medium, the dielectric medium is air, then we can write epsilon is equal to epsilon 0. So first, according to the formula, we have to calculate the field intensity. Because our main aim is to calculate the voltage. So what is the formula of field intensity? For it is already discussed that the field intensity for a cylinder is rho L 2 pi epsilon r into AR. What is rho L? Rho L is the linear charge density. Already I have discussed in the first slide that rho L is nothing but the, what is rho L? Rho L is nothing but the field intensity. Rho L is nothing but the line charge density, charge per unit line. So what is E? E is equal to 2 pi epsilon r. Now why r? Because when we are thinking about the intensity, the general tendency of the intensity to work in a radial direction, not the L means lengthwise. It always works in the radially, means it is always in the along the radius. So rho L is equal to 2 pi epsilon r AR. AR is the unit vector, the direction of the intensity, and it is according to the radius. Next, what is voltage? We know the voltage is equal to dV is equal to minus E dot dl. Voltage is equal to, voltage is a vector term. So dV is an E dot dl. So we are writing here. You can see from here that V is equal to minus E dot dl, from minus to plus, or we can tell from the far point to the near point. And you can know V is the far point is the outer surface, the plus means the inner surface, minus is the outer surface, plus is the inner surface. We are assuming actually from the far point to the near point. So we can see R is equal to actually B into R equals to A. R equals to A is equal to rho L. We are substituting the value of E here. Rho L 2 pi epsilon R into AR. As potential is working along the radius, the voltage will also work along the radius. So radius is dr and direction is AR. Now AR dot AR. This is the dot product and the magnitude is 1. And the result is a scalar quantity. So we can see here rho L 2 pi epsilon is constant. 1 by R, 1 by R, AR dot AR means it is 1. So 1 by R dr. You can see from this diagram, so it is the value V is equal to integration of rho L 2 pi epsilon R 2 pi epsilon R dr. AR dot AR is equal to AR dot AR equals to 1, and it is the unit vector. So what is rho L? So we can, and what is the sign? The sign is minus from the far point to the near point. Far point is B and near point is A. So rho L is constant, 2 pi constant, epsilon constant. If we write the constant here, 1 by R. 1 by R is equal to Ln by R. We can write Ln by R, or we can write also log base E. Both are correct. If you write log base E, that is also correct, but not log base 10. Maximum time we write only log, but that is incorrect. Log means log base 10. Either you have to mention log base E, or you will write Ln. So Ln A by B, minus sign is there, so it will be Ln B by A. What is capacitance then? Capacitance is equal to, according to our definition, Q by V. As this is a cable, so we will take the line charge density, and already we have discussed that the Q is equal to rho L. This is not cross product, this is the normal multiplication. So rho L into L by rho L 2 pi epsilon Ln B by A. So rho L cancel out, so it is becoming 2 pi epsilon L Ln B by A. So this is the capacitance of an coaxial cable. In the case of coaxial cable, capacitance C is equal to 2 pi epsilon L Ln B by A, whereas B is the radius of the outer surface and A is the radius of the inner surface. So let's do a small problem. Say a cylindrical capacitor having a length of 8 centimeter. So when the unit is centimeter, our first work is to convert it in the meter, because all the unit in our SI unit, and we will convert it into the meter form. So length is 8 centimeter, is made of 2 concentric rings. So it is like a cylinder. 2 concentric cylinders are there. Inner radius is 3 centimeter, A is 3 centimeter, and the outer radius means the radius of the outer circle is B centimeter. B is equal to 6 centimeter. Find the capacitance of the capacitor. So 8 centimeter means it will be 0.08 meter. 0.08 meter. What is the value? 0.03 meter. And this is 0.06 meter. So according to the formula of the capacitance, 2 pi epsilon 0 L ln B by A. So 2, what is the value of pi? 3.14 into, what is the value of epsilon 0? It is 8.854 into 10 to the power minus 12 into L. L value is, we got the L value as 0.08 divided by ln, or we can write it as log base E, ln B by A, 0.06 by 0.03. So we will get the value of the capacitance as 1.477 into 10 to the power minus 11 farad, or we can write it 0.144 microfarad. So this is the capacitance of the coaxial cable. Only thing we have to remember that, what we have to remember? We have to remember all the unit will be in meter, in SI format. Next one is the capacitance of a spherical capacitor. Same thing we will discuss here. The capacitance of a spherical capacitance. So what is the meaning of the spherical capacitance? Spherical capacitance means it looks like a ball. It looks like a sphere. It looks like a ball. Now if we give the positive charge on the inside, the outside there is a, if it is a concentric sphere, the outside there should be some negative charge. The opposite charge will be induced in the inner circle. And we are thinking there are two radius 1 and radius 2. Radius 1 R2 is the inner surface and R1 is the radius of the outer surface. So unlike the first one, we have to calculate the potential, and according to the definition, potential is equal to minus to plus means outer to inner. So R is equal to R1 to R is equal to R2. So we got the value R is equal to R1 to R is equal to R2. Or we can write R1 is equal to B. We can assume R1 is equal to B and R2 equals to A. So the value is B to A. Now what is the field intensity of a sphere? The field intensity of a sphere is Q by 4 pi epsilon R square. Q by 4 pi epsilon R square. This is the basic definition of intensity. Q by 4 pi epsilon R square. AR dot DL. Again, like the previous one, dl, like the previous one, dl is the length and the EMF will act according to the radius. So we can substitute it as the dr AR, dr AR, and AR dot AR equals to 1. So V is equal to integration of Q by 4 pi epsilon r square dr, and the distance is B to A. Now Q is constant, 4 pi epsilon is constant, minus sign, so minus of 1 by r square, r is equal to B to r is equal to A. So if we put the value, we will get Q minus 4 pi epsilon is equal to 1 by A minus 1 by B. 1 by A minus 1 by B. 1 by A minus 1 by B means the 1 by the small circle or inner circle minus radius of the big circle or outer circle. So this is the value of the capacitance of a sphere. First we will write that V is equal to E dot dl and E is equal to Q by 4 pi epsilon r square dot dr. Why? Because it will always works in the surface wise. So let's do a small problem like the before. So what is the plate of the capacitor have the radii 38 mm, and 40 mm. Calculate the capacitance. This is the first part. Calculate the capacitance. So already we got the formula. C equals to 4 pi epsilon AB B minus A by AB, which can be substituted as 4 pi epsilon AB B minus A. So we will use the formula here. What is the capacitance is given? It is given as B equals to, B is the outer one. B is the outer one. So which one is greater? 40. So B is equal to 40 mm. And we have to convert it into the meter. 40 into 10 to the power minus 3 meter. What is the value of A? A value is given as 38 millimeter. So 38 millimeter means 38 into 10 to the power minus 3 meter. Already we got this value. So what is capacitance according to the formula? So what is the formula? 4 pi epsilon AB B minus A. So what will be the value? 4 pi epsilon 0 BA. B means 40 into 10, 38, 10 to the power minus 3 into 10 to the power minus 3 by 4 pi epsilon 0. So they have directly wrote the value 4 pi epsilon 0. 8.854 into 10 to the power minus 12 into 40 minus 38 because B minus A. B minus A. 40 minus 38 mm means 2 into 10 to the power minus 3 meter. So if we solve the problem, we will get the answer 84.5 picofarad. Pico means 10 to the power minus 12 farad. Next, what must be the plate area of the parallel plate capacitor with the same separation of the capacitance? So if we make a same type of parallel plate capacitor, what is the formula of parallel plate capacitor? C is equal to epsilon A by D. What is the formula? Epsilon A by D. A is the cross-sectional area, D is the distance between them, and epsilon is equal to air. Nothing is mentioned, means it is free space or air. Now, so we know the value of epsilon, we know the value of D. What is D? D is nothing but what is D? D is equal to the distance between them. So already we have got the equation of the capacitor is this. So from here we can write AB is equal to C B minus A divided by 4 pi epsilon 0. And what is the meaning of A into B? A into B in the case of the parallel plate capacitor is the, what is this? This is the area of the plate, as this is the square in nature, rectangle in nature. So what is the cross-sectional, what is the surface area? Surface area is, if this is B, this is A, it is A into B. So we can write capacitance is epsilon 0 A B minus A, or we can also write like this. We know the formula. Capacitance is equal to epsilon 0 A by D. We know the formula. So what is the value of A? A is equal to CD by epsilon 0. Now what is the value of C? According to the question, with the same plate separation and capacitance, same capacitance. So capacitance value is 84.5 picofarad. What is the D? The distance between A to B, and it is basically 40 minus 38. What is epsilon 0? Epsilon 0 is nothing but the permittivity of air. So if we put the value, we will get the cross-sectional value is 191 centimeter square. So capacitance of the isolated sphere. What is the meaning of isolated sphere? Isolated sphere means, see, we are taking the example of the universe. A ball is kept in the universe. So what is the upper limit of the external sphere? There is no upper limit. So we can think that the B value R1 is equal to B, and this value is basically infinity, because we are assuming that we are bringing one point from infinity to one point. What is this? According to the definition, we are bringing one charge from infinity to the point. So B is equal to infinity. So in the formula 4 pi epsilon 1 by A, where A is the radius of the inner surface, A minus 1 by infinity. So 1 by infinity is equal to 0. So capacitance is 4 pi epsilon into A. So till now we have studied three types of capacitor: parallel plate capacitor, coaxial capacitor, and spherical capacitor. In the case of the parallel plate capacitor, we will now read about the composite parallel plate capacitor. So what is the meaning of composite parallel plate capacitor? Let's think about the underground cable. In the case of the underground cable, the outer surface is made of PVC, polyvinyl chloride. Inside, between the conductor and the PVC material, there are the different types of insulators. Different types of insulators means the layers of different types of dielectric medium, like impregnated paper, cotton, lead oxide. So different types of layer is given. Here we are assuming there are two things. One is epsilon 1, another one is the epsilon 2, and the distance between them is, the thickness is T1, which we can write D1 distance, and the thickness of the second one is T2, which can be written as D2. So what is T1 and T2? T1 and T2 is the thickness of the different types of material, different types of dielectric material. Now say we are assuming the total charge, if we connect it with a battery, if we connect the parallel plate with a battery, what will happen? There will be the charge, and if this is the positive charge, it should be the negative charge in the opposite side. And we are assuming that the Q is the charge on each plate. What is the field intensity of D1? Say this is our E1 and this is E2. What is E1? E1 is the field intensity in the region of D1, and E2 is the field intensity in the region of D2. So what is the V1? We know voltage equals to E1 D1. Voltage is equal to E into dot TL. This is our basic formula and we will use it everywhere. So E is E1 for the first case. For the first case, E is equal to E1 D1 and V2 is equal to E2 D2. So what is the V, total V? Total V equals to, total V means total voltage between the positive and negative sign is equal to E1 D1 plus E2 D2. So we got the value. Now we will think about the what is E1. E1 is equal to, according to the Gauss law, that E D is equal to epsilon into E. So we are thinking the permittivity of this medium is epsilon 1 and for this medium is epsilon 2. So for the case 1, D1 is equal to epsilon into E1. And what is D2? D2 is equal to epsilon into E2. So this is our, so what is E1? E1 is equal to D1 by epsilon 1. What is E2? D2 by epsilon 2. So what is voltage? D1 by epsilon 1 plus D2 by epsilon 2 D2. So this is our new voltage equation. Now, as we don't know the amount of charge, this is a surface charge density. This is a surface charge density. This is a surface. So we will think about the surface charge density. So say rho S. Rho S is the surface charge density. What is rho S? Rho S is the surface charge density. And according to this, the surface charge density is equal to D1 by D2. Why? Because according to the definition, rho S is equal to charge per unit area. According to the definition, rho S is equal to charge per unit area. What is D? D means the flux density. Psi by A. Psi is the number of flux and A is the cross surface area. Now, according to the Gauss law, what is the Gauss law says? The number of electrical lines of force equal to the charge enclosed. in a closed surface, the number of charge is equals to the number of lines of flux. So we can write psi, number of lines of flux, is equal to Q. So we can substitute it Q by A, and it is basically rho S. So we are substituting the value rho S is equal to D1 is equal to D2. And in the previous slide, we have already got that V is equal to D1 epsilon 1 into D1, D2 by epsilon 2, D2. Now we are substituting that D1 and D2 is equal to rho S. Now in any surface, the charge density is always constant. So we can write D1 by D2 is equal to D1 equals to D2 is equal to rho S. So we can write it here rho S D1 by epsilon 1 plus D2 by epsilon 2. We are using this formula here, rho S D1 by epsilon 1 plus D2 by epsilon 2. So what is capacitance? Q by V. Q we know, V value we know. So if we put the value, then what is the result? The result is, and what is Q? Q is rho S into A. Why rho S into A? Surface charge density into cross-sectional area. And ultimately we can get A is equal to, capacitance is equal to A by D1 plus epsilon 1 plus D2 by epsilon 2, like this. If we have n number of this dielectric material, we can write A is equal to D1 plus epsilon 1 plus D2 plus epsilon 2 plus D3 plus epsilon 3, like this. Now we are discussing about in the case, you can see one thing, in the case these composite materials are parallel to each other, but in the horizontally, they are in the horizontal manner. What will happen if the surface is in the vertical manner? So let's think, this is one plate, and the downside it is one plate, and the dielectrics are normal to the plane. This is one dielectrics and this is the another dielectric. So already we know E is equal to V by D. Already we know the definition. E equals to V by D, because V is equal to E into D. What is D? D is the thickness. D is the thickness or distance between the two parallel plates. D is equal to distance between two parallel plates. Now, what is the direction of E? Always E1 and E2, I told that we know it always works in the tangential form. In this case, in the previous case, we know, in the previous case or any case, they are always works in the radial direction. So E1 and E2 are both in the tangential form, and in the boundary condition tells the tangential components are always same, and so we can tell E1 by E2 is equal to V by D. In the previous case, if the parallel plates are in the horizontal form, E1 is not equal to E2, because both are differently working in the tangential form. But here both are like this. So in the boundary condition, according to the boundary condition, both tangential component of any normal EMF is same. And what is the value? V by D. So we can already know that D1 is equal to epsilon 1 and D2 is equal to epsilon 2. Already we have discussed these things. And what is E1? E1 is given as V by D. Here also E2 is equal to V by D. And what is the total charge? Total charge Q is equal to Q1 plus Q2. Already we know this one. And what is the Q1 and Q2? This is the rho S1. What is rho S1? Rho S1 is the volume charge density, surface charge density of this dielectric material. We are assuming this is rho S1 and this is rho S2. And as the parallel plate capacitor, is dividing the in a normal, so it is dividing the total cross-sectional area into two parts. In the before case, all slabs have the same cross-sectional area or same surface area. But in this case, the slabs are dividing the total surface area into two parts. One is A1, another one is A2. So for Q1, what is the charge density? For the Q1, the charge density is rho S1 into A1. What is Q2? Rho S2 into A2. Now what is rho S1? Rho S1 is equal to D1. We already know. What is rho S2? Rho S2 is equal to D2. So this is D1A1, this is D2A2. So what will be the Q? What will be the value of the Q? What is the value of the Q? Q is equal to epsilon 1 A1. This is our D. V by D means E. Here also epsilon 2 VA2 by D. So if we know the Q, if we know the V, what is the capacitance? Capacitance after substituting we get epsilon 1 A1 plus epsilon 2 A2 by D. This is the C1, this is the C2. You can see one thing here. You can see this is the formula of, whose formula is this? This is the formula of the shunt capacitor. It is the formula of shunt or parallel capacitor. And you can also check this one, that when current is flowing, it will go one line and another line. So both the capacitor are in parallel. If you think this one, you can see this is one. The current is flowing from here to here. So this is one line and this is another line. So it will behave like a series capacitor. So this is an example of also series. This is an example of the series capacitor. So this is the series capacitor and that is the shunt capacitor. Now we came to the last part. Energy stored in the capacitor. How, when as there is some voltage and charge is stored in the parallel plates, so there should be some energy. When plates are there and they are connected with the source, there should be some energy, and energy can be defined as the this is the energy, and we know that what is the energy? Energy is nothing but the work done. According to the definition, to bring one charge from one point to another point, we need to do some work done. So if the voltage across it is V, the battery is giving the voltage V, and the charge is equal to Q, the charge stored here is Q. So we can write Q is equal to CV. And according to the definition, what is work done? Work done means to bring some charge in a potential field from one point to another point. So dW equals to V into dQ. dQ means to unit of small charge. What is V? V is equal to, as we know, Q is equal to C by V. So V is equal to C Q by C. So we are substituting the Q by C here. So work done is equal to Q by C dQ. So what is the total work done? To bring the charge, zero charge to Q charge, to bring the Q amount of charge from one point to another point. So what is the formula? Q dQ. Q dQ means Q square by 2. So we are getting the value half Q square by C. So this is our formula 1. That is the U. The total energy stored is equal to half Q square by C. Now, what is Q by C? What is Q? Q is equal to C into V. So, if we put the value, if we write total energy U is equal to half CV squared by C, it is coming half CV squared. So this is the easy method to understand what is the total charge in a capacitor. The total charge stored in a capacitor is equal to half CV square. Now, if we want to tell the thing in the form of the EMF, so what is the EMF? For the same thing, we already know. If we connect it with the voltage V and the total charge is Q, we can write Q is equal to C into V. According to the another definition, work done is equal to half D into E. Why D into E? Because according to our definition, what is our basic definition? Work done. Work done definition is to bring the charge. And if we substitute this, we will get work done is equal to half integration through the volume of this D dot E dV. What is D? D is equal to epsilon of E. We got it from the energy stored in an field. If we go through this discussion, energy stored in a field, we got that energy stored in a field is always half volume integration of D dot E dV. So what is D? D is equal to epsilon into E dot E. So epsilon into E square. What is E? E is nothing but V by D whole square. V by D whole square. So what is the integration of volume? The integration of volume is we can write it is basically A into D. Why? We can write dV. We can write it as a dx, dy, dz. What is dz? Dz basically the height, the distance of the or thickness of the parallel plate. What is dx and dy? Dx and dy is equal to surface. Dx and dy is the surface. X and this is our y. So x and y is the surface. So we can write it as a ds, dz. So what is the total surface? Total surface is A. What is the dz? Dz is the distance. It is written as D. So it is coming half epsilon A by D into V square. So if we write the energy stored is equal to half epsilon A D V square. What is epsilon A by D? It is nothing but the capacitance. So half CV square. So we are telling this from the view of the electromotive field, that the energy stored in a field can be written as half volume integral of D dot E. This is the main thing to remember. So what is energy density? Energy density is nothing but the energy stored per unit volume. So this is the energy density. What is energy density? Energy density is the energy stored per unit volume is known as the energy density. Now we know the energy half CV square, we know the volume, we can easily get the energy density. So this is our today's class. We have discussed today about the capacitance. We have discussed about today the series capacitance and shunt capacitance. Then we have discussed about the parallel plate capacitor, spherical capacitor and cylindrical capacitor. Next we have discussed about the composite material horizontally and normally. And last of all, the energy stored in the capacitor. So thank you all.
Like, share and subscribe. Hit the bell icon for more updates.